Hello all. Good evening. So it's already 6:05. So I think we can start now. I'll be sharing my screen. Please let me know if my screen is visible. I hope you all can see my presentation.
Yes.
Yeah. Yeah. Okay. So welcome to week 6. Thank you all for joining. So in today's tutorial session, as Vinayak had asked in the previous class, I would be doing some of the previous assignment problems. So the first question is from assignment 2. It's question 5 in assignment 2. So they are asking, given that the diffusivity of elements at 900 degrees Celsius in silicon is this. So they have given diffusivity for gold, copper, phosphorus and iron, and we are asked to tell what is the which element will diffuse slower. So for that we need to understand what is diffusivity. So diffusivity is nothing but, in simple terms, just rate of diffusion. Sorry. So then naturally, if a diffusivity is the rate of diffusion, then whichever element will have the lowest diffusivity, that will diffuse slower. Is it fine? So then we just compare all these values and we see that phosphorus is 10 power minus 14. Compare that with 10 power minus 7 for gold and iron, and copper is around 10 power minus 6. So 10 power minus 14 is clearly much lower. So phosphorus will diffuse the slowest. Is that okay? Vinayak, this was one of the questions that you had a doubt in, right?
Yes, yes.
Now it's
Can
fine.
you explain once more?
Yeah, so they have given us the diffusivity. So diffusivity is nothing but the rate of diffusion. So it's the constant d in the diffusion equation. So basically it tells us how fast or slow, like by definition it means how fast or slow will the element diffuse in the system. So these are the diffusivity values that they have given. diffusivity at 900 degrees Celsius in silicon. So diffusivity is always defined for two things: which element is diffusing and in what material and at what temperature. So that and all those values they have given us. So diffusivity is the rate of diffusion. So whichever will have a higher rate will diffuse faster, and conversely whatever will have a slower rate will diffuse slower, or a smaller rate will diffuse slower. So we just compare these values and we see that 10 power minus 14 is the smallest value here. So phosphorus will diffuse slower. Is that okay?
Yes,
Yeah,
yes.
that's it. Okay, so next question is from assignment 3. So in amorphous silicon, for 10 power 18 centimeter cube concentration of dopants, the RP is nothing but projected range. Projected range is given to be 50 nanometer. Find the dose required. So projected range, by projected range we basically mean that till what range, okay. So this is my amorphous silicon, say. So I am putting dopants in it. So dopants will go up till some range inside the silicon, right? So that range they have given to be 50 nanometers. So this distance is 50 nanometers. Okay, so now they are asking, if I want so much concentration of dopants in this 50 nanometer range, what is the dose that I require? So dose, if you remember, so dose is nothing but integral of the concentration over the given range. So range is nothing but, say, if I say this is 0, so 0 to 50, or you can say uh, if this is 0, then this is 0 to 50, or you can say this is 0 and 0 to minus 50. Either ways the answer will be the same. So that is the equation for dose, and this was discussed in the class. So the concentration that they have given us, they are telling the concentration of dopants should be so much. So since they have not given us the concentration profile, let us assume that they require a constant concentration in this range, and then this concentration drops to 0 after this. So now let us calculate the dose based on this. So this is 50 nanometer. It will be 50 into 10 power minus, so this is in centimeter cube, so this will be 10 power minus 7, to ensure that our answer is also in centimeters. So this will come out to be 5 into 10 power 18 minus 6, 12 per centimeter square. Is that okay?
Okay, okay.
Okay, yeah, thanks. Okay, so this is from assignment 4. So this series of questions were like, I guess, in continuation. So in this, so this is for CVD. The mass transfer coefficient is given and surface reaction rate coefficient is given. So in CVD, if you remember, so we are depositing material on top of some substrate. So while we are depositing the material, it has to come and sit on top of the substrate, but there will be a boundary layer that is formed. Right. So there are two phenomena that happen here. One thing is the diffusion of the material through the boundary layer to the surface, and the second thing is the surface reaction. So they have given us the rates for both these processes. So they have given us the mass transfer coefficient that will determine how much material comes to the surface, and that is given by h equal to 10 centimeter per second, and the surface reaction rate coefficient. So this they have not given us the explicit value, but they have given us the formula. So surface reaction rate coefficient is given by this. So at 900 degrees Celsius, is the deposition rate limited by precursor vapor diffusion through the boundary layer or the surface reaction rate? So basically they are asking us to compare the rate of diffusion to the rate of surface reaction. So if the surface reaction rate is low, then that is the limiting condition. So the reaction is limited by the surface reaction, or the deposition is limited by the surface reaction. If the mass transfer coefficient is lower, then that means the diffusion is the limiting process here. So let us calculate what is K first. K is 10 power 7 times e power minus 1.9 EV by kT. So I don't think I am doing that here. So you can try it on your own. So this is 900 plus 273. So what the value that we get here is 0.606 something centimeter per second, and that is very less compared to H. So because of that we see that K is very less compared to H. That means the surface reaction is the limiting reaction. To understand this more quantitatively, we can a formula was given in the class that said that growth rate is P total times Y. Y is nothing but the ratio of the partial pressures. So yeah, so basically this entire term just means that the partial pressure of the precursor gas, that is flow, then upon N kBT times 1 by 1 upon H plus 1 upon K. So the growth rate, so when we are depositing a film, the growth rate of this film is given by the partial pressure of the precursor gas, that is understood, divided by N. N is the number of atoms, N is number of atoms of deposited material in a unit volume. So it is inversely proportional to that. Then kBT is the energy term, and then we have so 1 by H plus 1 by K in the denominator here. So whenever, in this case as it is seen, whenever K is very much less than H, we see that growth rate becomes P total Y on N kBT times so K is very small, so that means 1 by K will be very big. Compare that to 1 by H, 1 by H will be very small because H is very large compared to K. So then we will just have 1 by 1 over K, and it will give us a K here. Okay, so then the growth rate will only depend on the surface reaction rate. So that's why we say that it is surface reaction rate limited. Sorry, for some reason these options are wrong, but the question is the deposition rate limited by precursor vapor pressure diffusion through the boundary layer or the surface reaction rate? So the answer is surface reaction rate. Limited. Okay. I hope that makes sense.
Yes.
Okay, thank you, Raj. Okay, then one more question. I think we have two more questions from the assignments, previous assignments. So in this, a hot walled APCVD furnace has a tube diameter of 10 centimeter. So basically we have a furnace. This is 10 centimeters. And then they are saying that the hot zone length is 20 centimeters. So there is some heating here, and the length of the hot zone is given to be 20 centimeters. It is used to grow epitaxial silicon on a 3-inch wafer. So there is a wafer inside 3-inch at 800 degrees Celsius using silane precursor. The growth rate is 200 nanometer per minute. Okay, and then they were given us some values: molecular mass of silicon, density of silicon, molar volume, everything. So first thing that we need to calculate is silicon deposition rate in gram per minute. Okay, so since this is a hot wall furnace, silicon will deposit on both sides of the wafer, but as well as on the walls of the chamber, because it's a hot wall furnace. So yeah, so the reaction will happen at every place wherever it is hot. So first, to calculate the silicon deposition rate, uh, right, so first let us calculate the area. So area of deposition. So that will be nothing but, first of all, so first of all, it's the furnace. So furnace is 20 centimeter length, 10 centimeter diameter, so that is 5 centimeter radius, 2 into pi into 5 into 20. Okay, and then the wafer. So the wafer has two sides, so 2 into then pi r square, right? Pi into r square. So it was 7.5 centimeter diameter, so radius will be 3.75 square. So that many centimeters square is the area, and it turns out this comes out to be something around 768.3125 centimeters square. That is area of the deposition. Uh, so So right, now we have to find out how much silicon is depositing in gram per minute. So first let us find out. They have given us that the deposition rate is 200 nanometer per minute. So then we can, using this we can find out the volume of deposition. Well, the volume is given to be, it will be nothing but this times this, right? So volume of deposition per minute, let me write. So that will be 768 times 200 into 10 power minus 7. It will come out to be 0.0154 centimeter cube per minute. Right. So if you look here now, they have given us the density, that is 2.33 gram per centimeter cube. So in 1 centimeter cube we have 2.33 grams. So in 0.0154 centimeter cube we will have how much? So that will be nothing but 0.036 grams per minute. So that is the answer. Uh, the options, I think the closest option to this answer was 31.3 milligrams per minute. So that is the correct answer. Yeah. So based on the values of the constant and everything that we take, some decimal change might be there, but yeah, so this is the answer. So what we did, we first calculated the area of deposition, then we found out the volume of silicon deposited in 1 minute by using the rate of deposition, and then using the density we can find out how many grams of silicon were deposited in 1 minute. Next is silicon deposition rate in mole per minute. So that's simple. So many grams in a minute, so that means how many moles in a minute. So we know that the silicon molar mass is given to be, molecular mass is given to be 28 grams. Right. So 28 grams for 1 mole, that means 0.03 grams is how many moles? Is 0.03 into 1 by 28, that is equal to 0.0011 mole per minute. So that is the second answer. Sorry. The third part is minimum flow rate of silane. So each silane has one silicon in it, in standard centimeter cube per minute or SCCM. Right. So yeah, that is what they are telling. Minimum 1 mole of silane is needed for 1 mole of silicon. Okay, so we already know how many moles of silicon we require. So we just have to translate that to how many. Hello. Yeah. We just have to translate that to how many SCCM of SiH4 that we need. So for that we will use this value that they have given us. So molar volume is 22400 standard centimeter cube per mole. So that means that simply means that, so for 0.0011 moles we will require this times 22400 SCCM of silane, SiH4. So that will be nothing but something around 25 SCCM. Is that okay?
Yes, ma'am.
Yeah, thank you. Yes, so yeah, so now they are asking us, uh, so the growth rate is the maximum flow rate of the dilute silane from the cylinder flow controller is 1000 SCCM. Is it sufficient for the desired amount, that is 10 times the minimum pure silane flow? Okay, so the maximum flow rate is 1000 SCCM and the minimum silane flow that we calculated was 25. So technically this should be yes. According to me, I don't know why in the answer they have given us no, because 10 times 25 will be 250 SCCM. So 250 SCCM is definitely lesser than 1000, so that should be sufficient. But I guess the other TA will review the assignments again and then we will know the correct answer. And the next part is, if we keep the walls of the chambers cold, then obviously the area will reduce on which the deposition is taking place, then silicon doesn't deposit on them. In that case, will 1000 SCCM, yeah, like if it's able to do it even with the hot wall furnace, it will definitely be able to do with the cold wall furnace, because in the cold wall case we are not depositing on the furnace, we will be only depositing on the wafer. So yeah. Yes. So here uh, about the dilution of silane precursor, they are telling that it is generally diluted in hydrogen. But if the silane is diluted in nitrogen instead of hydrogen, the silicon growth rate increases. Why is that the case? So yeah, so yes, so let us read the options first. Nitrogen reacts with silane to form ammonia and silicon. Then second is dilution of silane in nitrogen instead of hydrogen avoids excess hydrogen. excess hydrogen in the chamber prevents hydrogen desorption from the surface. This rate limiting step is avoided. Then third point is nitrogen reacts with silicon in the wafer to form silicon nitride, which has very high volume compared to silicon. Hence, it appears as if the growth rate is increasing. Okay, so the correct answer here is the second option. So, uh, so what happens is whenever we are depositing silicon, epitaxial silicon, so at the top surface there will be some dangling bonds of silicon which are not satisfied. So what might happen is hydrogen might adsorb on these bonds, and it will take some energy to desorb this hydrogen to form H2 gas, and to take it out of the chamber. So when there is already hydrogen present in the so silane already has hydrogen, right, SiH4, and on top of that, if you are diluting it with more hydrogen, that means there will be hydrogen in abundance. So the partial pressure of hydrogen will be very high in the chamber, and so the desorption of hydrogen um, will take some energy. So instead, if we have nitrogen as the gas for dilution, so in that case there is no hydrogen present in the chamber, so only hydrogen that is coming from silicon, silane. So then because of less partial pressure of hydrogen, it will be easier to dissolve this hydrogen. So the rate limiting step is avoided, and that can be seen in these pictures or graphs that Prof had displayed in the lecture slides. So in the first graph we see the open site fraction. So as I told, right, so on the surface there will be some open sites, so there should be these open sites so that the silicon can come and sit on one of these sites. But if the hydrogen is passivating these sites, then there are fewer open sites, and we see that as the temperature is increasing, uh, the uh, the hydrogen adsorbing on these sites is increasing. That's why the open site fraction is reducing, and for a higher partial pressure of hydrogen, we see that there are even fewer open sites. So that is not good for us for depositing silicon, so because that will limit the silicon deposition rate. Similarly, we see here the growth rate of silicon versus SiH4 partial pressure. So at higher partial pressures there will be more hydrogen in the chamber, and so then the reaction will get desorption limited. Similarly, we can also see here, so in each of these diagrams, so the black triangles is silane in hydrogen, compare that to silane in nitrogen. So we see that the growth rate is higher for the same temperature. Okay, so those were the assignment problems that uh, one of you asked me to solve. Okay, is Vinayak still here?
Yes, yes.
Yes. Thank you. Uh, did you so? Is it clear now?
Yeah, yeah.
Yeah. Thanks. Okay, so I'm a little short on time today, so I'll just do a few more questions from the current week. Um, right. So let us begin with the first question. A positive photoresist is exposed through a mask using a I line, that is lambda equal to 365 nanometer source. Select the correct answer. So they have given us that it is a positive photoresist. Okay. So the options are exposed part of the photoresist would result in polymerization. Exposure increases the resolution of the exposed area in a developer, and exposure reduces the resolution of the exposed area in a developer. So again, this is a question regarding the definition of positive photoresist. So what do we mean by a positive resist and a negative resist? So in a positive resist, what happens is, so this is my substrate, and I'm coating it with a resist. Right. So this is done using spin coating methods that we have discussed in class. Um, so after I have coated it with resist, I'll expose it using this 365 nanometer light. So wherever it is getting exposed, those parts will either become more soluble in the developer, or they will become less soluble. They will harden and not become less soluble in the developer. So in case of positive photoresist, what happens is, so these regions will become more soluble in the developer. So when I develop this sample, what I'll get is something like this. So these regions will become open. So that's how we define a positive photoresist. So exposure increases dissolution of the exposed area in a developer. That is the correct answer. Exposed part of the photoresist would result in polymerization. Polymerization means hardening of the resist. Then this will be a negative resist. Similarly, reduces the dissolution of exposed area means negative resist. What kind of diffractions play a role in contact based lithography? So there are two types of lithography. One is projection lithography and one is contact based. So in projection lithography, there is a projection optics and the far field diffraction will play a role.
Both?
Um why do you say both?
No, sorry. Fed Nessel.
Fresnel, right.
Uh,
Yeah, so in this it is far field. This is it is contact litho, it's near field. So near field means it's Fresnel. Fresnel diffraction will play a role. So the third problem in litho, pre-baking of photoresist is an important step. So once we coat the resist, we need to bake it first before exposing it to the desired wavelength of light. Uh, so why is that the case? So select the correct statement. Pre-bake temperature, okay. Pre-bake temperature is same for low and high density resist. Glass transition temperature decides the pre-bake temperature. Pre-bake increases the resolution of the feature size. Pre-bake is done after the exposure of photoresist. So what do you think is the answer?
Glass transition temperature decides favorite temperature.
Right, you're right. So yeah, yeah. So the pre-bake temperature will actually depend on whether it's a low density or high density resist. So as it was discussed in class, so low density resist, in low density resist, it's easier for the acids to diffuse. So uh, like post exposure, there will be some chemical reaction that goes on in the photoresist, and that will create some acid, and that has to diffuse, but only to the required amount. So yeah, so the diffusion of that acid will depend on whether it's a low density or high density. So in low density, we usually prefer to heat it to a temperature which is below the glass transition temperature. Otherwise, yeah. And in the case of high density resist, we can heat it above Tg, glass transition temperature. So yeah, so that's why we prefer high density resist for when the addition is not a problem. When addition is a problem, we want strongly the resist to stick to the substrate. But when that is not a problem, we go for low density resist. There we don't heat it as much. However, yeah, so the exact recipe is decided using the glass transition temperature. Pre-bake increases the resolution of the feature size. Not really. Pre-bake is done after the exposure of photoresist. So that then it won't be pre-bake. That will be a post-exposure bake. So this is also not the case. Right. A photoresist contrast curve is shown in the following in the figure below. Identify the type of resist and calculate the resist contrast. So if we look here, at the higher energy, the thickness of the resist film is going down. So that means that wherever the exposure is there, uh, the resist has disappeared from those places. So that means it's a positive resist. So either this or this. And then we have to calculate the resist contrast. So resist contrast is given by a simple formula. Think log of, so where it has disappeared completely, E naught by E1. So this point and this point. So it will be 1 over 5, I guess. I Yeah, it's correct. So this is the correct answer. If you just calculate this, so this is log to the base 10. If you calculate this, you will get 1.43. So this is just formula application. Right. How does the thickness of photoresist coating depend on its viscosity? So, so that's just a mechanical process, right? Spin coating. So when we spin coat, if the viscosity is very high, then like so then it will stick, like it will be heavy to remove. So basically it will be directly proportional. Higher viscosity means there will be thickness will be higher for the photoresist. Low viscosity means the thickness will be lower. So yeah, like if you just imagine a wafer that is spinning, and then you have put a drop of photoresist in the center, it will spread towards the edges, and if it's not very viscous, it will just fly apart. But if it is very viscous, it will just make it to the end and stay there, so the thickness will be high. So then it is directly proportional. Okay, a process engineer patented the device using proximity based optical lithography. After the exposure and development process, so the engineer found metal ion contamination in the device. So what could be the source of contamination? So right, so what are all the processes that he did? He first spin coated the photoresist, then did a pre-bake, then did an exposure, then did a post-exposure bake, then developed it. Then he found out that there was some metal ion contamination. So the usual source of metal ion contamination is the developer. So developer can have Na plus or K plus ions. So it is possible that he chose a metal ion contaminated developer. So there are two types of developers, MIC and uh, MIF. So these ones are metal ion free developers. So probably he chose a metal ion contaminated developer. So metal ion contaminant developer. So that's why developer might be the reason that he saw that might be a source of contamination. What are the ways to prevent electromigration in metal semiconductor contacts? Okay, so this is about the metallization class that was taken by Sushobhan sir. Uh, what are the ways to prevent electromigration in metal semiconductor contacts? Okay, so if you remember, say this is my metal wire. It might so happen that so some part of this, so this is copper, so some part of this copper from one grain went and sat somewhere over here. So this usually happens because of all the, so when we are flowing current through this, so electrons, just by the momentum of the electrons, some of the metal, so some of the grains in the metal might get knocked off. So so the below layer is a semiconductor, right? So on top of that there is a metal. So this metal can get knocked off and can migrate to some other place when we are flowing current for a longer time through the same conductor. So, what are the ways to prevent this? So that is the problem of electromigration. So, let us look at all these options. First is to reduce metal grains. Someone is saying something?
Increase the line width of metal line.
Increasing the line width. Yes, you are right. Yeah. So, I forgot to mention that this is a multiple option correct statement. So, do you think anything else also will help?
I don't know the concept of kettling, but I think
I could not hear you. Let's go one by one. So, metal grain size. What will happen if we reduce the metal grain size? So, so these are two cases. So, electrons are coming from here. I am passing current from here. This is one case is with smaller okay, and the other case is with comparatively larger grains. So, what will happen in this case is there will be some force in the horizontal direction, but also some force that will be because sorry, this is force. So, that will be induced in the vertical direction because the electrons will get scattered. So, so these grains are oriented in random direction. So, there will be a induced vertical force. However, in this case, all the boundaries are perpendicular, like most of them will be perpendicular. So, this induced vertical force will be very low. Most of the force will be horizontal. So, because of that, what will happen is uh, if we increase the metal grain size, so if we reduce the metal grain size, so it is easier to knock off one of these grains from here and put them somewhere else, or like knock them off completely. So, because of this induced vertical force, so it is preferred to have bigger grain size. So, reduced metal grain size is definitely not an option. Increasing the metal grain size is an option. Second thing is increase the line width of the metal line. So, what will happen if I increase the line width? So, say I have one option small line width and second option very large line width. So, these are both metal wires, current is flowing through them. So, so the grains here, so say one of this grain gets knocked off, then the contact is completely gone, right? Because so this place will become like this is metal and there is no contact in the middle. However, if in this case if one of the grains get so one of the grain or yeah, one part gets knocked off, then we still have other parts for the electron to flow. It can flow around it, so there is more redundancy, more redundancy. So that's why increasing the line width helps. Also, having smaller grain size helps. Sorry, having larger grain size helps. Smaller grain size is easier to knock off. Larger grains are difficult to knock. Uh, and then this one more point is that using high melting point metals as barriers. So it is known that when the material or the metal through which we are flowing the current, if it is if the temperature is close to its melting point, it is more likely for electromigration to happen. So, if we have a higher melting point material, then uh, then that will mean that at the temperatures that we are working, the melting point is very high compared to that. So, the electromigration will be lower. So, using this also helps. So, uh, what do you mean as barriers? So, what we can do is we can have a barrier layer, so high melting point material barrier layer on top and bottom. So, what will happen is suppose one of these grains gets knocked off. So, this is not here, this part is empty. So, that will mean that uh, say both are not here. Okay, so the current can't pass through this, but then the current can still go pass through the barrier layer and go ahead. And it is very less likely that any of these grains will get knocked off, because this material has very high melting point, and at, because of that this material is very hard and it is difficult to undergo electromigration in this material. So 2, 3 and 4 are correct options. Is that okay?
Yes, ma'am.
Yes, thank you. State whether true or false. Sticking probability is nearly 1 for both CVD and ion implantation.
True.
True, you're right. Uh, so sticking probability, just for uh, so the sticking probability will actually follow a curve like this with respect to energy. So at lower energy processes like CVD or even physical vapor deposition, in some cases like evaporation, the sticking probability is 1. So because the energy of the process is so slow, so the material will slowly come, like through diffusion or some evaporation process, and sit on top of the material, so the sticking probability is high. If the material is coming at very high speed, also in that case, so like in ion implantation, in that case also it will stick on surface or even go inside the surface. However, in the case of intermediate processes where the energy of the process is intermediate, like in the case of sputtering. So in sputtering, what is happening is we have a target, we are hitting it with some ions, and due to the electric field, the sorry, not due to electric field, due to electric field we are hitting with ions, and then some material from the target will go and sit on the substrate. So this energy is intermediate, it is higher than evaporation but lower than ion implantation. So for these cases the sticking probability will be lower. So yeah, so that was it. So from that we know that the sticking probability is equal to 1 for sputtering deposition technique.
False.
Yeah, you're right. Choose from the following some of the effective ways to form ohmic contacts across the metal semiconductor junction. Uh, yeah, so whenever we are forming contacts with so using a metal on top of a semiconductor, the by default this contact is a Schottky diode like contact, because the work function of the metal is very different from the work function of the semiconductor. However, if we want to make an ohmic contact, what should we do? So there are some options. Annealing at high temperature to form silicide, using metals that gives high barrier potential with the semiconductor, increasing the doping of semiconductor at the interface, reducing the doping of semiconductor at the interface. Okay, so which all options do you think?
1 and 2.
1 and 2. Um,
2.
okay, okay. Can you explain me why 1? 1 is the correct answer.
When we form the silicide, it will basically gives the better chance to go them like titanium or tungsten.
Yeah.
And
Yeah, that is actually true. So instead of directly going from the metal to the semiconductor, the silicide will actually act as a uh, intermediate work function. So so the transition will be gradual, and yeah, that actually helps in getting ohmic contacts. Um, right. So okay, 1 is correct. What about 2? In 2, using metals that gives high barrier potential with the semiconductor. So why do we need higher barrier potential? That can you explain? Like because we usually to get ohmic contacts, mm, we want the difference in the work function to be low, right? So, won't
Yes,
high barrier potential actually make it more diode like?
I don't know.
I don't, yeah, I don't think so. This is the correct answer because, um, so, so what do we mean by an ohmic contact? Ohmic contact means that the voltage versus current should look like a straight line. But if there is a high barrier potential, mm, I really don't know how to explain this.
First, ma'am, if we use the high barrier potential, it will also help them to pass the current through them, like we see in the catalog.
Why? I mean, if the barrier potential is high, we'll need some
Ah, yes, yes,
energy. Only after that the current will start flowing. The graph will look something like this, not a straight line. Is what I think.
yes, yes.
I'll get back to you with a better explanation for this in the next class. Third point is increasing the doping of semiconductor at the interface. Uh, so yeah, so we want to reduce the work function difference between the two. So we know that metal is a very good conductor. So if we have a slightly good conductor region in between here by introducing doping, then that will act as a gradual change in the again phi. So yeah, so this actually helps increasing the doping of semiconductor at the interface. Yeah, so if you are having a highly doped region and then a metal on top of it, then that this acts as a ohmic contact. Then the fourth point is reducing the doping of semiconductor at the interface. So this will definitely not help. So that's it. I need to go now somewhere. If you guys have any questions, please let me know. Or if you want me to do some other assignment problems also, you can let me know.
No, ma'am.
Okay. Yeah, you can also write to me on email. For now, I'll be closing this class.
Okay.
Thank you so much.
Thank you, ma'am.
Thank you.
Thank you.